Hey everyone, and welcome. Today we're going to be detectives because we have a fascinating chemistry puzzle on our hands. We're going to solve the case of a very, very stubborn solid. So here's the mystery. Picture this. You mix a couple of things together, and suddenly a solid appears right when you don't want it to. Our mission, should we choose to accept it, is to figure out how to make it vanish. Now, it might sound like a magic trick, but I promise you it's all just really cool chemistry. And here is our main character, or maybe our main culprit. This is iron 3 hydroxide. This is the solid, the precipitate that just refuses to stay dissolved. Our entire investigation today is going to revolve around this one compound. Now, to solve any puzzle, first you've got to understand the rules of the game, right? So our first stop is diving into the fundamental principles of solubility. This is basically our rule book for cracking the case. Okay, so the most important rule in our book is something called the solubility product constant, or KSP for short. The best way to think about it is like this. You're dissolving sugar in a glass of water. Eventually, you hit a point where no more sugar will dissolve, right? The water is totally full. Well, KSP is that exact, scientifically defined limit for any given solid. It's the breaking point. For our specific case, this is the rule in action. Our solid, the iron 3 hydroxide, is in this really delicate balance. We call it an equilibrium, with its dissolved parts, which are 1 iron ion and 3 hydroxide ions. This is the balancing act that we need to learn how to control. And here's the math behind that rule. The KSP value is found by multiplying the concentration of the iron ions by the concentration of the hydroxide ions. And notice that little 3? That means the hydroxide concentration is cubed. This little formula right here holds the key to our entire puzzle. All right, so we have our rulebook, we have our formula, but this is where the mystery really deepens, because the first clue we uncover is something completely unexpected about the solution's acidity, its pH. And here it is, the first major plot twist. You'd think that dissolving a simple iron salt in plain water would give you a neutral pH of 7, right? Makes sense. But nope. In our case, the pH plummets all the way down to 1.434. That is incredibly acidic. So what in the world is going on here? Well, the reason is a neat little process called hydrolysis. You see, that positively charged ion is so attractive that it actually starts pulling apart the water molecules around it. This reaction releases hydrogen ions, those H+ ions, into the solution. And as you know, more hydrogen ions means a lower pH and a way more acidic solution. Now, using that surprising pH value, we can do our first real piece of detective work. We can actually calculate the KSP for our stubborn solid. And the number we get is, wow, it's tiny, 2.0 times 10 to the negative 39. A number that small just confirms how incredibly insoluble this compound really is. It desperately wants to be a solid. So our solid is tough, it's stable. And trying to fight this equilibrium head-on is probably a losing battle. It's time to change your tactics. It's time to call in a specialist. See, here's the crucial insight. We don't have to attack the solid itself. We just need to disrupt that delicate balance we saw earlier. So what if we could introduce something else into the mix that could tempt those dissolved iron ions, something that could lure them away from the equilibrium? And this is where we meet our secret agent, the cyanide ion. Cyanide is basically a supermagnet for iron. It binds to those dissolved iron ions so strongly that it effectively takes them completely out of the game by forming a brand new super stable complex. So what happens when our secret agent starts snatching up all the iron ions from the solution? Well, that equilibrium gets shattered. The whole system kind of panics, and to restore the balance, the solid iron 3 hydroxide has no choice but to start dissolving to release more iron ions. If we add enough of our secret agent, the entire solid just disappears. Case closed. But, our work isn't quite done. Any good detective needs precision. We know how to make the solid disappear, but now we need to figure out the exact conditions to prevent it from ever even forming in the first place. So, this brings us to our final challenge of the day. What is the absolute minimum pH we would need to keep all of that iron dissolved, completely preventing any of that stubborn precipitate from ever showing up? Let's walk through this together. It's actually pretty straightforward. We just go back to our trusty KSP formula. We plug in that tiny KSP value we found earlier and the concentration of iron that's given in the problem. From there, it's just a little bit of algebra to solve for the hydroxide concentration, and then one last quick conversion to get our final pH. And the answer is 2.8. That is the magic number. If we can keep the pH of that solution at or below 2.8, our stubborn solid will never even get a chance to form. Now that is some powerful predictive chemistry right there. So we did it. We solved the puzzle. But why does this one case matter in the grand scheme of things? Let's kind of zoom out for a second and look at the bigger picture. If there is one single thing to take away from all this, it's this. Solubility isn't just a simple yes or no. It's not some fixed state. It's a dynamic, shifting balance, an equilibrium that you can actually manipulate and control if you know the rules of the game. And believe me, this isn't just some academic exercise. Being able to control solubility is absolutely vital in the real world. We're talking about everything from purifying our drinking water and manufacturing countless products, to cleaning up environmental spills, and even designing the medicines that have to work inside our bodies. And that kind of leaves us with one final thought. We just saw how an invisible property like pH can have a very, very visible effect, making a solid appear from thin air or vanish completely. It just makes you wonder, what other powerful, invisible forces of chemistry are constantly at play, shaping the world we see every single day?